Yes, hello. This is the lecture on basis function. So we learned a lot about regression and classification, in particular linear regression and linear classification. So if we look at regression, linearity is often a good assumption when many inputs influence the data and every input only contributes a little bit. Also, some natural laws are approximately linear, like force equals mass times acceleration. But in general, in many real-world data sets, it's rather unlikely that a true function is linear. Similar in classification, linear classifiers often work well when many inputs influence the output and every input has a small influence. But also for classifiers, it is often not reasonable to assume that the classification boundaries are linear, hyperplanes. So there's a simple trick, but this trick is very fundamental to understanding more complex learning systems. And so I'm not sure how difficult it is to understand, but it is precisely very simple, but it might be difficult to understand all the different consequences of this trick. And so the trick is to simply transform the input into a high-dimensional space where then the regression classification might again be linear. Another view is, let's define appropriate features. So this goes in the direction of feature engineering. Another view is, let's define appropriate basis functions. And here's a typical example, and it's a classical XOR type problem, which sort of killed the perceptron in the late 60s. So the input pattern 0, 0 is mapped to a +1. The input pattern 1, 0 is mapped to a -1. The input pattern 0, 1 is also mapped to a -1. And the input pattern 1, 1 is mapped to a 1. And this is shown over here. So we have two inputs, x1 and x2. And for 0, 0, we have the output 1. For 1, 1, we have the output 1. For 1, 0, we have the output -1. And for 0, 1, we have the output -1 as well. And there's no way you can place this hyperplane that it separates the green examples from the red examples. So this is the classical example of two classes which are not linearly separable. And the trick is to simply add a third input. For the linear model, we had the inputs x1 and x2. But now let's consider x1 times x2 as an additional input. And this interaction term, x1, x2 couples the two inputs nonlinearly, because the one depends on the other. So it's a so-called interaction term. And here is how it looks like in 3 dimensions. So let's first look at 2 dimensions again, x1 and x2. And if we ignore the third one, then this one pops down also in this plane, and we have our old XOR problem. In these 2 dimensions, it's not linearly separable. But by adding this third input, x1 times x2, the fourth input, or the input here at 1, 1, the target is, or the input is now placed over here. Because x1 and x2 has the third dimension 1 here, and now the situation looks very different. For example, if we plug now the number in, so here's a function 1 minus 2x1 minus 2x2 plus 4x1 x2, and if we plug in 0, 0, this gives a 1. If we plug in 1, 1, this gives also 1, because 1 minus 2 is -3 plus 4, so this one is now active, gives you a 1. And 1, 0 is 1 minus 2. This is 0, so it doesn't have an effect. This is also 0, doesn't have an effect. So it's -1, and for 0, 1, you get the same. So this is a function now which goes through all these data points perfectly. And We call these different terms here now basis functions. So phi naught of x would be the constant, phi 1 of x would be x1 as before, phi 2 of x would be x2, and phi 3 of x would be this product x1 and x2. And of course we have weights or parameters in front of these basis functions, so it's 1 minus 2 minus 2 plus 4. Here's an example how a hyperplane would look like. So it is now sort of tilted in this space, and you see that the minus ones are sort of on one side of this hyperplane, and the plus ones are on the other side of the hyperplane. So in this three-dimensional space, we can indeed find a linearly separating hyperplane. We just couldn't do it in the original space. Or here, it's another view in space at x1, x2. We now have these separating constructs here, and they place plus and plus on these quadrants and minus on these quadrants. Or this is how it looks like if you plot it as a three-dimensional function. You see that if you plot the function, it will now have a nonlinear behavior. Remember before, this f of x always was a linear function of the inputs as well. Or I think we called it h of x before. And the same with functions. So here we have one input and one output. And this is a typical behavior. For small inputs, you have a more or less linear behavior. But if you go to very positive or very negative values, you see this nonlinear behavior. So it assumes the form of a so-called sigmoidal curve, which is a name for this type of behavior. And here we can also add basis functions. So here the first one is 1 again, the constant, the 0 one. The first one is x, the second one is x2, and the third one is x to the power of 3. And we can get the weights 0, 1, 0, minus 3. So this is then the function x minus 0.3 times x to the power of 3. And this is shown over here. And if we put the weight on them, we can perfectly fit this desired function. So the same trick here by adding additional inputs or additional constructing additional basis functions. We have a representation where a linear model, the linear model then finds the weights 0, 1, 0, minus 0.3. Can lead to a prediction which exactly fits the target function. So the basic idea is really simple. So we just add inputs. So in addition to the original inputs, we add inputs that are calculated as deterministic functions of the existing inputs, and we treat them as additional inputs. So one popular example are so-called polynomial basis functions. So here we have the, let's say, original inputs, 1, x1, x2, x3, and then we add x1, x2, x1, x3, x2, x3, x1 square, x2 square, x3 square, and even more if you want. And these functions are called basis functions. So this is our notation. So phi m of x from and m goes from 1 to m5. So m5 is always the number of our basis functions. And in the example, it's phi 1 is 1, phi 0 is 1, phi 1 is x1, and phi 5, for example, is x1 times x3, and so on. But independent of the choice of basis function, the regression parameters are calculated using the well-known equations for linear regression. So that's why it's a trick. No? You transform it into another space, and then you have this same old simple problem already we have a good understanding of. So you can draw it as a architecture or as a network architecture, and in the future we will draw neural networks often in this way. So here in the bottom, and that's a sort of standard that we start at the bottom, we represent the inputs, so x1 to xm. So sometimes we have also the 0 or the 1 represented, sometimes not, the constant. Then we calculate all these basis functions. So phi 1 of x to phi m phi of x. And this is fixed, that's why I call it fixed, fixed basis functions. So we have some insights of what good basis functions are, that's what it means. So you can also think of this as a pre-processing step from green to blue. And now we have our old linear system. So we form a weighted sum of the basis functions and I call this now f of x. And maybe f of x is already the output. Then we have a regression problem. Or we apply some form of nonlinearity. Then we have a classification model. So very simple, but that's it. Yeah, and this applies to classification and also linear models. Not sure what the point here was. Oh no, the point here is you don't have to do this additional inputs. You could also define your original inputs as basis functions. And in this case, the first basis function would be 1, the second one would be x1, and the mth one would be xm. So in this case, the inputs straight away go through the basis functions, and they're just constant, and then x1, x2, x3, xm phi, just to make you understand that also a system with only linear inputs can be thought of as a basis function system. So this is a review of from the lecture of linear regression, just to remind you of the equations. So we had multiple inputs. We had the constant here, and then W naught, and then a weighted sum of inputs, and we wrote it in this convenient form, x transposed W, or you can also write W transpose x. The same thing. And we often use the regularized cost function or penalized cost function. This square of the difference between the target, so the training data target, and the prediction squared, plus lambda, some regularization parameter, and then sum over the parameters squared from 0 to m if we have m parameters. And we derived the least square solution, which gave us this equation here. So the penalized best solution for the parameters is x transpose. So this was the design matrix. X transpose x plus lambda I is the identity matrix. The inverse of this expression times x transpose times y. No, y was the vector of targets. X is the design matrix. And we have exactly the same equations, only that we replace the x by the basis functions. So the prediction of a system with fixed basis function has also a W naught, and the sum. Now the sum is not over the inputs, but the sum over the basis functions, and the weights are on the basis functions, and these are the basis functions calculated based on the inputs. So if you want, you can also give this a name, Z or something, and then it looks exactly like before. We can also write down the regularized cost function, which is now a sum over the target value minus the output of the basis function system. So it's a linear system, only that this x is replaced by phi of x, sum over all data points squared plus lambda. And now we have the sum from 0 to number of basis functions, Wm squared. And the solution is exactly the same as before, only that x transpose x is now replaced by phi transpose phi. And it's plus lambda I, inverse of that, times phi transpose I, and this phi has as many rows again as there are data points, and the columns are different now. They're not the original inputs, but they are the outputs of the basis functions. So phi1 applied to x1 to phi m phi applied to x1. The last one is phi1 x applied to xn to phi m phi applied to xn. So this design matrix changes, but the equations for solving or for finding the best parameters are exactly the same as before. And in the regression, this is also simply the output, W0 plus weighted sum of the basis functions. And in classification, we can put a sign in front and then just look at the sign of this expression. And we can apply perceptron learning rule if you want after the transformation of the inputs to the basis function representation. So this seems simple and maybe seems a little bit too simple because now we have challenges. The one is to find problem-specific basis functions which are able to efficiently or effectively model the true mappings. And we hope that the true dependency f of x can be modeled by at least one of the functions out of the basis function class we are considering. Of course, if you add too few of them, we might not be able to model the true nonlinear dependency. If we add too many, we have many parameters to fit. Although we will see in the lecture on kernels that it is possible to work with an infinite number of basis functions by applying another trick, the kernel trick. So we already learned about polynomial basis functions. Another class of basis functions are radial basis functions, or RBFs. And a typical representation is a Gaussian basis function. So the Gaussian is calculated in this way. You take your vector input x, you subtract some other vector of the same dimension, Cj. You take the difference, you take the magnitude squared of this difference, you divide it by 2s squared, take the minus of this expression and put the exponential in front. So if you have never seen this, this is Gaussian distribution. And this is the jth basis function. So often it's only characterized by a different mean value, mean parameter here. So this is how it looks like in practice. Remember, C is the center. So if this is the center C in one dimension, and this shows a nice Gaussian curve, and S here has a interpretation. It's the standard deviation here. So in some sense, the width of this Gaussian. So if you have a small s, then it's a very sharp Gaussian. If you have a big S, it's a very broad Gaussian. And in 2 dimension, it looks similar. So this was x and y. This is now x1 and x2. So we can plot y. Y would be perpendicular to the plane. So we have a vector C. The center puts the Gaussian basis function at this location, and S is sort of shows you also sort of the shape of the basis function. That is a sort of circle of equi-amplitude of the Gaussian. Or if you want to look at it in this picture here, so this is how it looks like. Now, so you have a mean again, and the function has its maximum at the mean, and then it drops off to the distance if you go away from the mean. And this also applies to high dimensions. So here's an example in 1 dimension. So 1 input, 1 output. And this is the function we want to model, this pink function over here. These are our 3 basis functions. So we have 3 of them. And if we put appropriate weights on top of, or multiply these basis functions with the appropriate weights, we can get a perfect fit for exactly this behavior. This is a pretty nonlinear function, and we only need 3 basis functions. There's an interesting comment. So this looks a little bit complicated. So we have only one input, x, and this is the class labels we want to have. So here we want to, in the left side, we want to have the green label. In the middle, we want to have the red label. And on the right side, we want to have the green label again. And so this cannot be separated in one dimension with a linear classifier, obviously. So then I introduce these 2 basis functions. These are 2 Gaussian basis functions. As a function of x, they have this behavior. And now we plot it into the phi space. So this is the space from x to y. This is the space of x1 of x and x2 of x. And if we move here from left to right, the basis functions, or the output of the basis functions behave like this. So they are on this strange looking, what is called a manifold. So let's see. So if x is very small, then the phi 2 is very small, and phi 1 is sort of in the middle. So that's where we start here. Then if we move to the right, phi 1 becomes larger, and also phi 2 becomes larger. So this is happening over here. Then phi 1 becomes smaller, if we move to the right, and phi 2 becomes larger. So we're in this region. And then on the right side, everything becomes smaller again, and we end up here. So this is how, if you look at the basis function space, how the data look like. So even if in the original space the data might be randomly or arbitrarily spaced, in this basis function space we have this pretty interesting curve, which has, I mean, since this had one dimension, this also only has 1 degree of freedom. So it's called a nonlinear manifold with 1 degree of freedom. And if we place in this space our separating hyperplane, then it can be this one. On the right side, so this would be this region, we might classify as red, and on this side we classify everything as green. So this simple trick of transformation into basis function already generates some interesting spaces or interesting representations. Yeah, so far all seems to be too simple. So here's the catch. In some cases, the number of important or sensible basis functions increases exponentially with the number of inputs. Let's say in one dimension we need A RBFs, so maybe A equals 10. And we want to maintain the same complexity in higher dimensions. Then we need A to the power of m RBFs. So if A equals 10, then we have 10 to the power of m. And this is a really large number for even relatively small m's. And the same problem occurs when we use polynomial basis functions. The number of possible combinations, if we allow for all possible polynomials, increases also exponentially. So the important challenge is, how can I get a small number of relevant basis functions? So the possibly very small number which still is able to capture the behavior of the function we are trying to model. So here's an illustration. So in one dimension we have 10 RBF type of basis functions that we can model a certain smooth function over here. If we want to have the same smoothness, we need already in 2 dimensions 10 to the power of 2, which means 100 RBFs, and this goes up if you increase the dimension of the input space. Yeah, and this is the so-called Bellman's curse of dimensionality, or one form of it. If you increase your dimensions, the problems become intractable. And in a way, this was the situation before neural networks came about, because fortunately we can solve some of these problems. And this will be the topic of the next lecture. But there are also some, you just have to place Gaussians everywhere. The two strategies are forward selection and backward selection. So in forward selection, you start with a linear model, then you add a basis function sequentially, and each step you add the basis function whose addition decreases the training cost the most. So it's a greedy approach. And this was done by one of the really early classifiers, which became used in a real-world application in optical character recognition. And this was developed by Jürgen Schürmann from AEG. And it was, I think, in the 70s or so already a product of AEG. And now, of course, it's used everywhere in the postal system. So start with pixel-based image features, these handwritten digits. Then you do a dimensionality reduction via principal component analysis, which we'll cover later. And then you add a linear classifier. You start with a linear classifier and add polynomials that significantly increase performance. And then at the end, you apply a linear classifier. So this is fast, simple, works well, and was in fact a very important application. It's called polynomial classification, and we used in postal automation, AG, and then later Siemens and other companies. You can also do the other way. You start with a model which is too complex, and then incrementally decrease complexity. You first start with many basis functions, then you stepwise remove basis functions. At each step, you remove the one which decreases or increases the training cost the least, because of course, if you have a lot of them, you have the smallest training error, and if you remove some, training costs increases. So it's also a greedy approach. Yeah, of course, this is not optimal because we have this greedy behavior, and to find the best subset of k-basis functions is in fact NP hard. So that's impossible, and these type of heuristics can work already quite well. So an example is placement of advertisements in on your web page when you open a web page. Here features are handcrafted, so engineers in these companies, they design always new features. So maybe they use some features based on your personal profile. They use a feature derived from the search query you use to find this page, and maybe many other things. So typically a couple hundred, and then the prediction of the best advertisement to show you is based on this. It's just a linear system, more or less, based on these handcrafted features. Because also speed is important in these applications. You want to have a system which acts very quickly, and you also don't want a huge memory trace. So then these systems work quite well and important. So there are different ways. I hope you understood the simplicity and the basic principle. And it's very important that you understand that, because the rest of the lecture builds on that understanding. And it's really simple, but as often the consequences can be quite powerful, but also sometimes then again difficult to understand what is going on. So you can think of it as a form of prior knowledge, because the prior assumption is that your function can be modeled by the basis function you are assuming. So if you assume Gaussian basis functions, you assume that the function can be modeled by a sum of Gaussian basis functions. If you assume polynomial basis functions, the same is true for polynomials. Then the data can favor certain members of basis functions of a function class. And an interesting extension is a lecture on kernel systems, where we will see that the set of basis functions can be even infinite. But also, there's an interesting transition to neural networks because they are using sort of smart basis functions. So this was it. Thank you very much, and see you in the next lecture.